Have you ever wondered what really happens at the very edge of a mathematical function? Not where it is, but where it looks like it's going? Well, today we're going to demystify one of the most fundamental ideas in all of calculus, the concept of a limit. Let's dive in and explore what happens right at the edge of mathematical possibility.
So here's our game plan. We'll kick things off by looking at a strange little mystery, a hole in a graph. Then we'll introduce the tool we need to solve it, the limit. After that, we'll see how to actually find one, figure out what happens when paths just don't meet up, and even tackle functions that shoot for infinity. And to wrap it all up, we'll see why this whole idea is so incredibly important for understanding reality itself.
All right, so let's set the scene here. Most functions are pretty well behaved. You give them an input, they give you an output. Simple. But some functions, they have these specific points where they kind of break down, where they're officially undefined. And as we're about to see, these breakdowns can look very, very different.
And that really is the million-dollar question, isn't it? To see what I mean, let's look at 3 different functions that are all undefined at the exact same spot, x equals 2. But as you're about to see, being undefined can mean totally different things. We're talking everything from a simple little hole to a sudden jump to a launch into deep space.
First up, check out this graph. See that? It has a tiny hole in it. The function is completely undefined right at that one point. But if you trace the line with your finger from either side, you're heading toward the exact same spot. It's like a bridge with just one single plank missing. We can see exactly where that plank is supposed to go.
Okay, now for our second case. This function is also undefined at x equals 2. But here there's a problem. There's no agreement. If you follow the graph from the left, you're heading down towards -1. But if you come in from the right, you're heading up towards +1. The two paths they don't meet up. They create this sudden, jarring jump.
And here's our third and final mystery. This function doesn't approach a single number, or even 2 different numbers. No. As you get closer and closer to x equals 2, from either side, the graph just goes vertical. It rockets up and up, getting bigger and bigger forever. It's a completely different kind of undefined behavior.
So, we've got a hole, a jump, and a rocket ship. Clearly, just saying the word undefined isn't enough. It doesn't really tell us the whole story, does it? We need a more precise tool. We need a way to talk about the intention of the function. And that tool, my friends, is the limit.
And this is the absolute key idea right here. A limit isn't about what happens at the point. In fact, most of the time we don't even care if the function is defined there at all. A limit is all about the journey, not the destination. It's that single value the function is getting infinitely close to as you sneak up on your target.
And this is how we write it all down. Now I know, it looks a little fancy, but I promise it's pretty simple. LIM just stands for limit. That part underneath, the x arrow A, just means as x gets closer and closer to the number a. And L is that special value, the limit, that our function is zeroing in on. It's the language we use to describe what a function is trying to do.
Okay, so that's the what. But how do you actually find a limit? Well, we're going to start with 2 really intuitive methods that are kind of like detective work. We're going to gather clues from a table of values and then inspect the scene of the crime, the graph itself.
The table method is all about sneaking up on your target. All you do is pick numbers that get incredibly close to your point A, but you do it from both sides, a little bit less and a little bit more. Then you just calculate the function's value at each of those spots and watch for a pattern. Are the results from both sides closing in on one single number?
Let's try it for the limit of sine of x over x as x approaches 0. Now this function is undefined right at 0, but just look at the table. As we come in from the negative side, the values creep up. 0.998, 0.9999, 0.99999, and as we approach from the positive side, we see the exact same thing happening. The evidence is pretty overwhelming here.
Both paths are basically screaming the number 1, and we can confirm our hunch by looking at the graph. The picture of sine of x over x shows that same familiar hole we saw earlier, but it's sitting precisely at a y value of 1. The numerical clues and the visual evidence match up perfectly. The limit is 1.
But wait a minute. What about that jumpy function from the beginning? The one where the paths didn't agree at all? To handle that kind of situation, we need a slightly more nuanced tool. We need to talk about one-sided limits. See, we can actually ask about the limit from just one side at a time. The limit from the left, which we show with that little minus sign, only cares about what happens when you approach from numbers smaller than a, and the limit from the right, with the plus sign,
only cares about the approach from numbers bigger than a. It lets us describe each path completely independently.
And this right here leads us to the single most important rule about limits. Seriously, for a general two-sided limit to exist, one condition is absolutely non-negotiable. The limit from the left and the limit from the right must both exist, and they have to be equal. If the paths lead to different places, the overall limit simply does not exist. Period.
Okay, now let's circle all the way back to our third and final mystery. That function that just shot right off the graph. This is another case where the limit doesn't exist, but for a different reason. It's because the function doesn't approach a finite number at all. Instead, it just grows and grows without any boundary.
You remember this guy, right? As we squeeze in closer and closer to x equals 2, the function's values they explode. They don't settle down near a number, they just increase without bound. We call this behavior an infinite limit.
To describe this, we use the symbol for infinity. Now, this is really, really important to understand. Infinity is not a number. It's an idea, it's a concept. So when we write that a limit equals infinity, we are technically saying the limit does not exist. But we're also describing how it doesn't exist, by growing uncontrollably large.
So what does this look like on a graph? Well, it creates something called a vertical asymptote. Think of it like an invisible vertical wall that the function gets infinitely close to but can never ever cross. It's a boundary that the function just rides up or down forever.
So, after all this, I know what you might be thinking. Okay, this is interesting, I guess, but so what? Why does describing holes and jumps actually matter in the real world? Well, it turns out that limits are the language we use to describe the fundamental boundaries of our physical universe. Just take a look at this table. It's based on Einstein's theory of relativity. It shows what happens to an object's mass as its velocity, v, gets closer and closer to the speed of light, c. At 99% the speed of light, its mass is already over 7 times what it should be. At 99.99%, it's over 70 times normal. You see where this is going?
What you're seeing is a limit in action, in the real world. As an object's speed approaches the speed of light, its mass approaches infinity. The universe literally has a vertical asymptote at the speed of light. And since no object can have infinite mass, this limit proves that nothing with mass can ever reach it. It's a physical impossibility, described perfectly by the language of limits.
So you see, limits aren't just some abstract exercise for math class. They're the tool we use to precisely describe behavior right at the boundary, whether it's a tiny hole in a graph or the ultimate speed limit of the entire cosmos. They allow us to explore the very edge of what's possible, which makes you wonder what other fundamental rules of our universe are just waiting to be described by the power of calculus.